All right, we want to show that the nilpotent elements are an ideal, and if you mod out by them, then you don't have any non-zero nilpotents anymore. And that kind of makes a little intuitive sense because when you mod out by something, you're like collapsing things, and so basically you would expect that if you mod out by the nilpotent elements, you sort of collapse them all into one, and they'd all be contained in just the zero element. So, anyways, so proving that this is an ideal, let's see here. Let let A and B be an N. And so say that A to the N and B to the M are all equal to 0. I don't know why somehow we got on the mathematicians use N first and then M for using natural numbers. But M, L, M, N, M comes before N in the alphabet, so I don't know why that is, but whatever. Then by the binomial theorem, so we're going to use some stuff that you might have to refresh on, but anyways, if you take the sum, so we want to prove that this is an ideal, so we want to prove that's closed under sums, and if we raise it to the power of n plus m, then we're going to show that this ends up being, we want to show that a plus b raised to some power is 0, and we're going to show that this happens to be the right power to raise it to. So here we've got this binomial coefficient. Yeah, a to the n plus m minus k, then b to the k, and this is equal to the sum. I'm going to break it up. N plus m over k, a to the n, a to the m minus k, b to the k, because you can break up exponents like that. So that's if we go from k equals 0 to m. And what we're highlighting is we're highlighting this guy. So if k is going from 0 to m, then n plus m minus k is at least n, and so we can always pull this guy out. What about when k is bigger than m? Then we get n plus m for k, then we keep the n plus m minus k, and then this, here we get b to the m, and then b to the k. So this bm comes out here because this k over here is at least, oh wait, no. Oh wow, I messed this up in the, oh no, this is right. But this is wrong. Yeah, no, I messed this up. We have to subtract m, right? Because the exponents, no, right. So k equals m, so when k equals m plus 1, the original thing, we would have b to the k, which would be b to the m plus 1, and what we want is we want that b to the m, and we want the b to the 1. So, yeah, over here we need a k minus m here. Yeah, so I'm kind of reading off a solution that I gave back a while ago, and I messed this up here. But yeah, so the fact that we have this a to the n here is 0, and this b to the m here is 0. And so if we write the sums out like this, we see that every term is 0. So a plus b is an n. Let's see here. I'll keep those circled just to make them a little more clear. If r is in R, then if we take the element AR, to the n. This is a commutative ring, remember. That's really important here because we can just bring all the a's together and all the r's together. And so this a to the n is going to give us 0. But this is also r to the n, a to the n, which is, because of commutativity again, ra to the n. So AR and RA are both in n, hence n is an ideal. So now suppose we have an element r plus n in R mod n. And suppose r plus n is nilpotent. Now what does that mean in the set R mod n? This means r to the n is in n for some n in n. Because what you would need is because r1 plus n, r2 plus n is equal to r1, r2 plus n in R mod n. That's how we define multiplication here. And so we want that product needs to belong to an element of n in order for it to be the 0 element in R mod n, and so we need r to the n to be in n for some natural number n. See here. So r to the n is nilpotent, and I'm kind of expanding, I'm elaborating more than necessary on here. So r to the n to the m equals 0 for some m in n. So r to the nm equals 0, so r is in n. So see here. So r plus n equals n. And that confirms that any nilpotent element in R mod n is precisely the 0 element, which is n. And so there we go. This completes our proof.